Hello everyone. So welcome to our first lecture for physics where we are going to start a new chapter. Right? Last time we did a lecture where we understood how to use the log tables. Okay, and today is the first lecture where we are going to start a chapter. So we'll just begin with a quick understanding of what is there in physics and how is it related especially to engineering. So what's the difference between physics and engineering? So in physics, what we do is we basically study various laws, right? Or basically we study the science. Okay, physics is the study of science. It's a part of science. Whereas in engineering, what we do is whatever we learn in this subject of physics or other branches also as well. So this science, these laws, right? Whatever we learn, we make machines out of them, right? So physics is the understanding of the science behind the machine. Okay. So in engineering, right, if you see there are different subjects of or branches of engineering. There is civil engineering, there is electrical engineering, computer engineering, right? Mechanical engineering, okay, there is aeronautical, automobile, right, chemical, biomedical, all and several more if you just search on Google. Right? These are all different branches of engineering. So amongst all these branches, right, a very important branch is electrical and electronics engineering. And the chapter that I'm starting today is related to this branch of engineering. Okay, and the name of the chapter is current electricity. Okay, in 11th standard, it is also called as electric current through conductors. Okay, so there are two names. Basically, if you see the NCERT syllabus, right? So in this chapter, what are we going to study? Right? It's mainly we want to deal with the circuits. Right? There will be circuit diagrams. There will be components. You can see here. This is a circuit diagram for it's an actual circuit PCB for a motherboard, right? Which is a part of your computer, right? The main component, one of the main components of your computer. So like that, we will also be dealing with different circuit diagrams. Okay. So NCERT, this chapter is there in the 12th standard, okay, entire chapter. But for our board, HSC board, this chapter is split into half. Half of the chapter is in 11th standard, half of it is in 12th standard. So that's why I'm starting this chapter today. Okay. So what about the exams, right? Is it important from the exam point of view? What is the exam weightage? So NEET and JEE, both these exams, JEE mains, right, and NEET, there are going to be 3 MCQs. MCQ is for multiple choice questions, right? In NEET and JEE exams, all right, a question is given to you and there are 4 options, A, B, C, D. You have to select which one is right. So in both these exams, there are going to be 3 questions, and each question in both the exams is 4 marks each, right? So 4 into 3 will give me 12 marks. And you may think, okay, 3 questions, 12 mark, is it that important? Well, 12 marks can change your rank, to the extent that you may land up in a different state. Okay, it's very important. It's a very important topic. Also, since it is there in the 11th standard, you need it for your college exams. Okay, 12th standard, definitely we need it for the board exam, right? And very important point here is in the 12th standard board exam there will also be practicals, right? Practical exam, the board practical exam, which is carrying quite a high weightage, right? As per the current paper pattern, it is 30 marks of practicals. So in these 30 marks of board practicals, right, you see the practicals, there are usually in your journal, you will see there are 10 practicals, 5 in physics 1 and 5 in physics 2. This chapter current electricity belongs to what we call as physics 2 part 2. So there are 2 experiments from this chapter which are a part of those 5 experiments. Okay, so that's what is important about this chapter. So let's begin now with a very simple understanding of what you have learned in school, right? You know the components, Ohm's law, resistor, current, voltage, all these things you have heard about it. So let's begin with a simple example. Okay, so what I have here, what we call this is a resistor. Okay, the symbol, right, is you can see here up and down lines like these, right, which denotes basically opposition, right? Resistance. The word resistance means opposition. Symbol for it is R, and to this resistance, or let's call it as a resistor, okay, to this resistor I will connect a cell. okay, and this cell has a voltage, we can call it as E, or if you want you can call it as V. This plus line here, the bigger line, right, is the plus symbol, and the minus sign here is for, right, the smaller line. So let us connect this cell to our resistor through wires. Okay, if I connect the cell to the wire through the wires to the resistor, what is going to happen is, I know from the positive of this cell current will start flowing, right? So I can say the current starts from the positive of the cell, right? It goes through the resistor, and finally the current enters back into the negative of the cell. So I can say there is a current which is flowing in the clockwise direction. Okay, current is flowing in the clockwise direction, right, from positive of the cell to the negative of the cell. But I can also say that there are electrons which are flowing from the negative of the cell to the positive of the cell, right? In fact, you have studied in school, right, current and electrons, right? What do they mean? So what exactly is current, right? So we say current is nothing but the flow of electrons. The flow of electrons is called as current. And what exactly is the direction for current? We say that conventional current flows opposite to that of the electrons. So if you still didn't get the point, if you see I'm highlighting the terms here in blue, current is electron, but current flows opposite to electron, right? Just if you just repeat the statement, you will see, right, there is a problem here. Current is electrons, but current flows opposite to electrons. So can I say these are basically contradictory statements? If current is electron, right, then how can it flow opposite to electron, right? If today is Monday, then how can today be Tuesday? Today is Monday, today is Tuesday. These are two contradictory statements, right? Today is Monday, tomorrow is Tuesday. That's fine, but today is Monday, today is Tuesday. These are contradictory statements. So similarly, current is electron, but it flows opposite to electrons. This sounds contradictory, right? So we need to do something. We need to resolve this contradiction. Okay, what is the understanding here? Let's see. So we will start talking about flow. Okay, flow of what? It can be flow of anything. Okay, it may be flow of water. We will talk about it, right? All these examples we are going to discuss a little bit in detail. Flow of water, a flow of heat, okay, a flow of air or wind, you can say, right? Or need not be something from physics. We can take an example out of physics. Let's say there is flow of knowledge. Okay, so these examples, if I analyze them in detail, I can understand, I can categorize flow into two types. Okay, first I can say is a natural flow. Okay, what's a natural flow? Natural flow is supposed to be automatic. It happens on its own. I don't need to do anything. I just have to give it an opportunity, right? Versus the second category I can say is artificial flow. That means it's not going to happen on its own. It's not automatic. It's artificial, right? That means some external energy has to be given. Some external energy has to be supplied. It's needed, without which this flow will not happen. Okay, so let's take an example of water. Okay, so if I take a bottle of water and if I just turn it upside down, you'll see water will spill. Or another example for water is, suppose you open the tap. So when you open your tap, water starts flowing, right? So can I say this is a natural flow, automatic flow, right? I don't have to do anything. Just as I said, give it an opportunity, means open the tap. So can I say water is flowing from a high level to a lower level? Okay, water flows naturally on its own, automatically, from a high level to a low level. Okay, and what about the low to high flow? Is that also possible, right? So where is that water, when you turn on the tap, open the tap, where is that water coming from? Okay, so that water is basically coming from the overhead water tank, right? And where did the water come from? Into the tank, right? So that water came, right, from the municipality, right? There are underground water pipes which connect to your building, to your society, and then there will be a motor, a pump, right, which will pump up the water. It has to take the water to the height, to the terrace, and from there it's going to flow on its own, right? So that is an example of external energy needed, right? Unless I turn on my motor, or if the pump goes bad, right? If it doesn't work, that day you won't get water, right? So if I want a low to high flow, it is possible, okay? But external energy is needed. Let's take an example of, say, heat, right? This is a flame here, but I know it's just to denote heat. So how does heat flow? Can I say it naturally, automatically on its own? It flows from a high temperature to a lower temperature object, right? High temperature object to a low temperature, usually let's say it's the surrounding, right? So if I take a cup of hot tea and I place it on a table, right, then after some time I will notice that the temperature goes down. So that's a high to low flow, high temperature tea to low temperature surrounding room. Whereas, is low to high flow possible in the case of heat? Yes, that is also possible, right? But then again, external energy is needed. So if I take a cup of water, and I just put it for, just keep it on a table, it's not going to get heated up. If I put it on the stove and turn on the stove and use the chemical energy, convert the chemical energy into heat energy, then yes, its temperature will go from low to high. So that is an example of artificial flow. Same is in the case of wind or air, right? Why do we need fans in a room, right? Because there is no airflow. So naturally, how does air flow? Okay. Or sometimes, you may notice if you open a window, suddenly, you will see a gush of air coming in. So why is air flowing? Naturally, automatically, right? It's from high pressure to low pressure, automatic flow, right? And again, the reverse flow, low to high, is also possible. But then again, as I said, you will have to probably turn on the fan or do something like that, right? Some energy has to be given. So same is the case with, this is an example where, not from physics, like, why are you hearing this lecture, right? So there is a flow of knowledge which is happening, right? Some information, something new you are learning, right? So can I say your knowledge level right now is a little bit low and we want to make it high? So external energy is needed. If you were not hearing this lecture, you would not have understood these concepts, right? So that is an example of artificial flow, right? But once you learn everything, like you just did your 10th standard, right, from grade 1 to 10, you have finished your exams and now you are sitting at home. So do you need to watch some videos to forget everything? Okay, so that is again an automatic, naturally on your own you are going to forget everything, right? Or if not forget everything, at least most of the things I can say, right? So because that's a very natural high to low flow, your knowledge from high level will come down to low level on its own, naturally, automatically. Okay, so now what we can do here is, these terms high and low, we can just denote them by symbols. So what are the symbols we use? Very simple. You can just use the plus symbol for something higher, right? Plus, more, high, and the minus symbol for something low, at a lower level. Okay, so plus, so minus is for low and plus is for high. Now coming back to our example, right? So we have our resistor connected to the cell, all right? So electrons are flowing. So is the flow of electrons here, is it natural or is it artificial? Think about it. Okay, so I would say it is natural. Why? All I have to do is turn on the switch. Once the switch is on, the flow will start on its own. I don't have to do anything. So the electrons, I can say, are flowing here from the negative, right, to the positive. So here negative means what? The electrons themselves are negatively charged. So if I have more electrons at a particular place, I will have to put the minus sign, and what it means is there are higher number of electrons, more number of electrons here. So here more does not mean plus, it means minus. Okay, and they are flowing towards a place where I have put a positive sign. This positive here does not mean that there are more electrons. This positive here means there are less number of electrons, or effective polarity is positive, right? Or basically it means there are less number of electrons. The number of electrons are low. So the electrons are having a very natural flow from high to low. But the problem with electrons is, which does not happen with water or air or the examples which we considered, heat, knowledge, all these things, is plus and minus have only one meaning there. Plus means high, minus means low. Whereas here, plus can mean positive, and plus, if there are less number of electrons, right, the electrons are less, then it's low as well. So how can plus be low? That is what is creating a confusion here. So how do we resolve this confusion? Very simple. Define a new term called as current. So what is this current? Or let's say it flows opposite to that of the electrons, right? So that means it is flowing in this diagram, it is going to flow in the clockwise direction. So, you know, as you can see here, from the positive of the cell to the negative of the cell. And henceforward, stop talking about the electrons. Just talk about this word current. So what is it in reality that actually flows from the positive of the cell to the negative of the cell? The answer is, it's nothing. Okay, it is nothing that actually flows. So it's the current which is flowing from negative to positive. Okay, so what's the use of all this information that we are getting here? Okay, is it of any practical use? So let's take an example. Okay, and we will study here our cell. So what do we mean by a cell? Okay, all of you have used, you know, you are using cells all the time, right? We put them in remote controls or torches or wall clocks, right? So here you can see there is a Duracell or Eveready. These are very standard brands. Okay, you can have some made in China cells as well, or you know, any kind of a rechargeable cell or a battery that you may use in any Bluetooth device, right? A mouse or a keyboard or whatever. Okay, there is car batteries, right? Car batteries are you know, they are also, what's the difference between a battery and a cell, right? These are, earlier ones are called as cells, and these are all the car is called as a battery. So what's the reason for that? Okay, so the reason is a combination of cell is called as a battery. Okay, so car we call as a battery, and whereas all these are cells. And you also have a cell, right, or a battery which we can use in our cell phones, cellular phones, mobile phones. Okay, so we have our same example, right? The resistor connected to the cell, current is flowing in the clockwise direction. Now for a few minutes, let's just change the symbol for the cell. Usually you see we keep a very small gap between the plus and the minus, the big and the small line. Now purposely for a few minutes, I'm changing the symbol. So is current flowing? Is current flowing through this cell, inside the cell? Yes. What's the answer? Answer is yes, it is flowing. Why? Current has to flow. Why? Because for current to flow, there has to be a closed path. Current cannot start from the positive of the cell, okay, go around and come here and stop at the negative and then that's it, end of it. No, it cannot happen that way. There has to be current flowing from the negative to the positive also. So then the question arises is, what type of flow is there within the cell, inside the cell? Okay, so you can see very clearly here the direction is from minus to plus, or in other words, I can say it's an artificial flow. The flow of current inside the cell is from minus to plus, it is artificial. So that means I will need some energy. There has to be some loss of energy, some energy has to be supplied, somebody has to give some energy. So who is giving that energy, right? What type of energy are we talking about? Okay, what is the type of energy that is being used up, that is being supplied? Okay, so it is nothing but the chemical energy. The chemicals inside the cell, they are being used up, they are getting exhausted over a period of time. No matter what device it is, you will have to either throw away and put new cells, or you'll have to recharge it. Why? Because this chemical energy is being used up. Okay, so the idea here is we have to account for this loss of energy. Okay, हिसाब में लेके आने का है, we have to account for it. So what do we do? How do we deal with energy in physics? So this is going to be a common thing in several MCQs throughout the subject. Okay, energy is very commonly dealt with in physics. So what do we do about energy in all the MCQs? This is what I'm going to do. We will compare energy with wealth or money. Okay, why? You will see it helps us, right? There is a chapter called as work, power, energy. It will help us tremendously if we do this comparison. So money exists in different forms, right? What are the different forms of money? So there is cash. Okay, nice bundles of cash. You can have gold. Gold is a form of wealth. Okay, credit card, plastic money we say, or maybe some real estate, some nice house or plot of land you have. Okay, these are all different forms of wealth. And nowadays, there is this cryptocurrency, bitcoins, right? That is also a form of wealth. Shares, mutual funds, so many, right? All these are forms of wealth. So just like these, right? Well, just like wealth is in different forms, similarly we all know that energy also is in different forms. Okay. So what are the different forms? There is kinetic, potential, heat, light, sound, electrical, nuclear, right? Several more you can just search on Google. So what energy is getting lost here in this our circuit diagram, right? It is nothing but chemical energy. Okay. So, but this loss of chemical energy you will study in detail actually in electrochemistry, which is a chapter in chemistry, not in physics. Here in physics, what I'm really interested in is not the chemical part of it. Okay, I'm not interested in the chemical part of it. I'm interested only in the energy part of it. So what I can do is, since I have just like money in different forms, energy is also in different forms. So just for the sake of accounting, okay, I'm going to use heat energy. So how do I show heat in a circuit? Right, very simple. Just draw a resistor. Why? Because when current flows through a resistor, and there is current flowing inside, right? So if current is flowing through a resistor, we all know from 10th standard that that's what is called as Joule's effect, right? That is heating effect of current, right? I square RT is the formula for the heat generated inside a resistor when a current I flows through it. So since this resistance is inside the cell, okay, the name we give it is called as internal resistance of a cell. Okay. And the symbol we give it to distinguish it from this capital R, right? Capital R is different, small r is different, right? So that's the way we distinguish it. Capital R is the external resistor, small r is the internal resistance. So what is it? It is it a real resistor that you will find inside a cell? If you cut open a cell, will you find this resistor inside? No. It is simply, as I said, it is a representation of that loss of, actually speaking, chemical energy, right? It's a representation, like plastic in reality, right? Plastic is not money, but credit card is, right? It's a representation of the money that you have in your bank or the bank is willing to give you, right? It's a representation. So similarly here, the small r is a representation of the loss of energy. So we come back to our original symbol. We will not keep such a big gap between the positive and the negative terminal. We'll keep a small gap, and you can draw this resistor outside, and just by writing small r, it's obvious that this resistor is the internal resistance. Okay. So again, the question still remains: what is the use? Why are we studying all this, right? Why should I study internal resistance? Is it of any use? Okay, please remember, everything you study in science, not just physics, right? In science, there is some practical daily life application. That's the reason we are studying. Otherwise, there is no point studying it. We are not wasting our time here. Okay, so we need to understand what is it about. So again, what we can do is we'll take some example in terms of numbers to see what's happening here. Okay, so this cell whose voltage we wrote as E, okay, let's say it is 2 volts, and that external resistor to which it is connected, which in practically speaking, say it's a toy car, or it's a remote control, or it's a wall clock, or whatever, a wristwatch, all these places we use cells. So let's say it is of 1 ohm resistance, and let's assume that the internal resistance is also 1 ohms. Okay, I'm just taking very simple numbers to make a point here to understand what's happening. So can we find out the current through this cell, right? Through this circuit, you can say it's just use Ohm's law. I is equal to V by R. The voltage is 2. Total resistance is 1 plus 1, 2 ohms. So I'll get 2 by 2 is nothing but 1 ampere. Okay, and so just to summarize, we have capital R and small r both equal to 1 ohm, and we have a 1 ampere current flowing. Now, how much voltage is developed across the individual resistors? Let's find that out. So again, we can use Ohm's law. V across the capital R is I into capital R, which is basically 1 ampere into 1 ohm is giving me 1 volt. And the exact same thing for the small r, right? V across the small r, the loss is again 1 ampere into 1 ohm is again 1 volt. So we got some numbers here. There was 2 volts, right, which split into 1 and 1, right? Again, we had 2 volts of the cell which became 1 and 1 across the 1 ohms, 1 volts across 1 volt across the 1 ohm resistance, right? So the number 2 and these two numbers 1 volt each, what are they? So this 2 volt is what we call as EMF. You might have heard in your school, depending on the board in which you were. Okay, EMF, it stands for electromotive force. Okay, we'll talk more about it later on. Then the 1 volt that we get across the capital R, the resistance, the external resistance, is what we call as PD. PD stands for potential difference, which is also a voltage. Okay, so please note, EMF, the name is electromotive force, but it's not measured in newtons or dynes. It's a voltage. Okay, and the PD is also a voltage, and the 1 volt of voltage which is across the internal resistance, we can call it actually as a loss. Why is it called as loss? The reason is we are not going to use it, right? It's within the cell, right? It is in fact, that's what we were saying, there is loss of energy, right? So we have 2 volts EMF, 1 volt PD, and 1 volt of loss. So can I say that 2 is basically 1 plus 1, or in other words, EMF is PD plus loss, right? The voltage that was given was 2, and what was consumed across the each resistance was 1 volt each. So EMF is PD plus loss. This is our formula which we are going to use to solve several MCQs. Okay, when we start solving in the next lecture, you will notice we are going to use this formula. Okay, or what I can also write it is as instead of EMF equal to PD plus loss, I can say, bring the loss in the LHS, I can say EMF minus loss is equal to PD. So what exactly is this EMF? Right? There is a textbook definition and there is a practical definition. So first I'll give you the practical definition. The name is electromotive force. It's a voltage, and we are going to call it as the voltage that is printed on the label of the cell. Every cell has a label. On the label you will see some voltage printed, right? And PD is nothing but the voltage, the actual value of the voltage that is found across the cell. If you take a voltmeter and just measure the voltage across the cell, that's what is called as PD. Okay, so again, voltage printed on the label is EMF, and voltage, actual voltage across the cell, is what we call as PD. And what about the textbook definition? What are you going to write in the exam, in the college exam if it comes? Okay, so EMF is defined as the work done to move a unit charge once around the complete circuit. Why are we using these words, right? Unit charge, so I'm going to use 1 coulomb. Complete circuit, what does that mean? That means EMF is nothing but 2 volts, right, which was 1 volt plus 1 volt, right? So again, work done to move a unit charge. So 2 volts is 1 volt plus 1 volt, so that 2 volts is the 1 volt external as well as the 1 volt internal, both. That's why I'm using the word complete circuit. Work done to move a unit charge once around a complete circuit. Whereas the work done to move a unit charge once across the external load only the capital R, across the external resistance, that is what is called as potential difference. Okay. So again, if you look at those cells which I had given you, right, the car battery, if you see carefully, the voltage is printed on the label, right, 12 volts. Usually all car batteries are 12 volts, right? Or if you take those made in China cells, you will again, and even the Duracell and Eveready, if you see carefully, you will find the voltage there. Usually the pencil cells, we call them as AA, AAA, right? These are all standard sizes. They are 1.5 volts. And this is your cell phone, right, battery. And again, you can see here it is 3.7 volts. So all these numbers, right, they are nothing but the EMF. But actually what you are going to get is less. You are not going to get the voltage that is printed on the label. Example is, suppose you take a pen drive. If you buy a brand new pen drive, let's say 64 GB SanDisk, I'm just giving an example. Plug it into your computer and immediately don't copy any file, just check properties, right click properties and see the memory. Available space would not be 64 GB. It will be less than 64 GB, like something maybe 62 or 63 GB, right? So just like that, what is printed on the label is different, what you actually get is different, right? So we started the whole discussion by talking about energy, but then suddenly we are talking about loss of voltage, right? Or we compared it to loss of memory in the case of a pen drive. So why is that? Very simple, right? Because voltage is proportional to the energy. You had a formula in 10th standard, right? Again, it depends on your which board you were in, but most of the boards had this formula in 10th standard. V is equal to W by Q, and that's why the textbook definition is work done per unit charge, right? W by Q. So the V is proportional to W, the work done, or which we call as energy, right? So voltage is proportional to energy. So the question still remains, right? Why am I still studying this? What's the use of all this information? Okay. So we said EMF minus loss is PD. Okay. So let's compare the cells which we took. So we had a Duracell and a Eveready. What is the difference between these two cells? Right? If you go to a shop, any stationery or a chemist shop in India would they sell these products, right? So just go and ask them, you say you want to buy a Duracell or a Eveready. What is it that you are going to notice? Okay, technically the difference is Duracell has very less loss. This loss here, okay, this loss here is very little, whereas Eveready has a little bit more of loss, right? That means what? The actual PD that you are going to get in Duracell would be more. The PD that you will get in Eveready would be less. So the idea here is that there is less loss of energy in Duracell. That means whatever chemicals are there, they are getting exhausted, but slowly, not so quickly, not so rapidly as in case of a Eveready. And because of this, what is it that you are actually going to notice here, right? When you go to buy a cell, what is it that you are really concerned about? It's not the EMF, it's not the PD, it's not the internal resistance. What is the number that really matters, right? Is the cost, right? Duracell is very expensive, more than 40 rupees for one cell. Eveready is around 13 or 14 rupees for one cell, right? It's cheap. And if you go for made in China products, you can get a full packet of cells for maybe 10 rupees, right? It's dirt cheap, you can say. What is the difference between these three cells, right? I'm not promoting any brand here, okay, but the idea here is about internal resistance, right? The MRP, the maximum retail price of your cell, is nothing but inversely proportional to the internal resistance. The more the loss, the less that cell will last, and lesser should be its cost, right? The lesser the internal resistance, right, the more will be the time for which you can use that cell, right? And that's why you can say its price would also be more, right? And that's why the high price for Duracell is really justified. Okay. So just a small note for the 12th standard, right? We are not going to discuss this in the 11th standard, but I'm just mentioning it here because in 12th standard we will talk about it. We said that EMF loss and PD, the relationship is EMF minus loss is PD. Okay, this usually happens when you are using the cell. But in 12th standard, we will also notice that we can say EMF plus loss can also become PD, right? So you can have plus EMF plus loss is PD, or you can even have EMF minus losses. Both signs are possible, okay? And the reason is the plus sign will be used when the cell is being recharged. As I said, the chemicals will get exhausted. So once the chemicals get over, either you throw it away, or if it's a rechargeable cell, you have to recharge it, right, by passing reverse current through the cell. So during that time, there is a loss of energy for the supply voltage, and that loss is getting stored inside the cell in the form of chemical energy, right? So more details of it, we will talk about it in 12th standard. As far as the MCQs are concerned, right now in 11th standard, we are just going to use EMF minus loss is equal to potential difference, okay? So in the next class, right, I'm going to start with the MCQs, okay? Please don't miss the next class. It's going to be a nice introduction to the MCQs. How do we deal with MCQs in physics? And then we will continue with these examples of numericals on internal resistance of the cell, okay? So that's all for today, okay? See you in the next class.